Hi, welcome to the ZP Developer Zone. We do this every Thursday at 8 a.m. London time, but today, because of a whole series of meetings, unfortunately, not unfortunately, but we have gone live early. But we use this Developer Zone to answer questions that came into the week. I'm going to talk fast. There's about 7 questions here, and I just literally have to jump into it. Don't forget the ZP Academy. It gives you free advice. Don't forget our webinars. We do them every Thursday. We do have collaborations running in the UK and Norway. We have been hiring of recent. We do have a ZB Developers on website. And we do have our workshops. Now on the workshop front, we just had a workshop. In fact, we had a workshop in September, and I'm delighted that there's 2 guys coming from Australia in September. So these are international workshops, and people are literally flying halfway around the globe in order to come to them. So these workshops are about IVDs and biosensors in general. We do have workshops in the UK as well. But if you see a link, I will later today make sure that I put it onto the underneath the video so you can find the link. So we have workshops, we have conferences. Now talking about conferences, we do have our big Scandinavia Sensor Summit, which makes a lot of sense because the 2 guys who are coming from Australia, for example, they're coming to a really comprehensive workshop on biosensors and CGMs and molecular assays. They're coming on the 11th and 12th, and then because they've come in such a long way, they're going to stay for the 13th and 14th for the conference. So thanks to those guys. And here's a link to the conference. Now in terms of questions, question number 1, how small a change can I measure with a glucose sensor? Question number 2, how do I convert current into concentration? The answer to question number 1 is it can probably be quite small, but if I was going to give you and I consider this a conservative answer, 0.1 millimolar. Number 2, how do I convert current into a concentration? You come up with a calibration curve. I'll show you how to do that. Question number 3 is really linked to number 2. You create what's called a standard curve with glucose signal or current versus concentration. I'll describe that. How to modify or how to 3D modify an electrode. So if you have a new material and you consider that it has some, let's say, special properties, then I think actually 3D printing onto a traditional, let's say, screen printed electrode is a good way of kind of doing that step change and showing that you have some increased performance. And it also gives you a complete electrochemical cell in a form factor that's, let's say, applicable at least to the IVD market, in vitro diagnostics market. And is one step closer to being compatible or demonstratable to the wearables market. Number 5 is about genetic testing. Genetics can mean RNA, DNA. Well, genetics is strictly speaking DNA, but when people talk about genetics testing, they kind of mean molecular assays. So I'll talk about RNA, DNA assays. Somebody else wants a working electrode, wants a screen printed electrode where the carbon is working. So where the working electrode is carbon and the counter electrode is carbon. And they actually want silver chloride as the reference electrode. I'll deal with that. Somebody else asked, have we heard of LMP 91000? And should they use it? The quick answer is we have used it in the past. I do not recommend it these days. There are much better chips. I would look at the more modern open source potentiostats. I actually think the world has changed. That open source potentiostats, it's an interesting kind of university exercise, but actually there's so many good chips out there these days that it's more about programming than doing electronics. Anyway, I will discuss it. Yes, we have heard of it. And by the way, if you're going to use a ZP sensor with your own open source potentiostat, the potential that you need to apply at the working electrode versus the reference electrode is 650 millivolts. All right, question number 1. How small a change can I measure with my glucose sensor? So this is standard data off our website. So this is like a standard curve. Here's a link to it. This is me zooming in on it. And I know it's a bit sort of crude, but I'm sort of zooming in and saying, okay, that step there constitutes 10 millimolar. So if I just sort of imagined a little step, then I could probably argue to myself that actually I can resolve 0.1 millimolar. The resolution that you'll get depends on how well you set up the experiment. If you set up an experiment and have bad connections, then you'll have noise, and so it'll be hard to resolve these little steps. But you should, really be able to resolve 0.1 millimolar of glucose. So I sort of essentially wish you good luck with it. And I will sort of plow into your next question. Your next questions 2 and 3 are really kind of linked. I just showed this curve. This is a kind of standard curve of current versus it says time, but it's actually versus it's also concentration, because this is 0 millimolar, 5 millimolar, 10 millimolar, 15, 20 millimolar. We would do this, we call this a staircase experiment. It's actually an interesting question, because I realized we do this experiment in our workshops, but we also have a lot of YouTube videos about how to measure a CGM and how to measure a glucose sensor. So we do have them on our YouTube channel, but this is the standard curve. There was a link to it on the previous slide. Simply, we can now construct it. This is 0 millimolar, so I should have put that, that concentration there is 0 millimolar, that's the current. By the way, the Julie software, we have a Julie demo on the 5th of September. Try and Google Julie demo webinar, and you'll see us actually do this kind of analysis in real time. And we're going to hold 2 webinars on that day, so there's no excuses. There's one in the morning, one in the afternoon, to cover both sides of the globe, or east and west on the globe. Then you measure at this concentration, and we plot that again. So essentially what we're doing is we're plotting concentration against time. We do a simple linear regression, and we get our signal. So we get our calibration curve. So then when we detect an unknown solution or measure an unknown solution, we just look at the current, and then we can read off the concentration. And that's how to convert current into concentration. Question number 4. So you've got a new material. It may be 3D in nature. How do you kind of show its stepwise improvements to people like ZP who are interested in IVD and are also interested in wearables? I'd say take a standard electrode like this. I've obviously linked to it here. These electrodes are really sort of super cheap, so it actually allows you to break them and destroy them whilst you develop your process. You've got to have a low cost electrode in order to do this. And you can get a signal like using ferrocyanide. And I do have a link to that kind of solution below, but this is a fairly standard electrochemical procedure. So you baseline yourself just using standard chemicals, then you modify it, and when you modified it, I suspect that the peak height here will go up, and I suspect that the peaks will shift. The reason they'll shift is because you're pushing more and more current through the circuit, and you'll suffer from something called IR drop. You can actually then instigate IR compensation. For me, it doesn't matter too much. I know what the phenomenon is, I don't mind, but people do get a little bit concerned about it. But what I'm saying here, not concerned, if they're publishing papers in academic journals, they would get concerned about it. If you're a sort of pragmatic industrial electrochemist, you don't get too concerned about it because you know what it is, and you can mentally deal with it. As long as my signal is versus concentration, I'm quite happy. So if I was to go backwards slightly on this, so you've got a new novel material. You want to show that it's, let's say an improvement over just a 2D electrode. So a 2D electrode, for example, would it be a screen printed electrode like the one I've linked to here? You would just characterize it, if you were producing a paper or publishing a paper, and then you would 3D print over the top of it. Just the fact that you're 3D printing something that may be conductive will probably increase the surface area. So then I suspect the signal, as I say, will go up and may slightly shift due to the peaks might slightly shift due to IR drops. That's my kind of prediction. Now, if your polymer is not highly conductive, then maybe the signal will actually just shrink down. But that would be the kind of start of a validation of those new materials. In terms of equipment, you may need a potentiostat with EIS capability, electrochemical impedance spectroscopy. We just find EIS is super useful. You will need a sheet of these. This sheet is what we call perforated, so each electrode can be popped out. You will need a sheet of those. You will need a cable to go between the potentiostat. This is what I've linked to, is the cable that goes between that potentiostat, which is an EIS version, and you need a connector. This connector, if you're using ZP's potentiostats, our banana plugs, which are here, have 2mm banana plugs, and therefore I've sort of given you a link to a connector which has a 7mm slot, which will take our screen printed electrode with 2mm female banana plug orifices, so you can plug the cable into it. So that would be the kind of setup I'd recommend. And if you know, if for whatever reason, if you want to sort of source the ferrous cyanide from us, you can also source that from us as well. I'll try and put all links underneath the video to help people navigate to this stuff. How can I say that a little bit quicker? Question number 5, right? So somebody wants to make a multiplex genetic assay, which may be RNA, DNA based. I mean, it's probably worth saying that at ZP we've done a lot of point of care development of these kind of molecular assays, you know, and in the molecular assays there's often a sort of amplification step, and that could be PCR, it could be LAMP. We've also done sort of molecular biology using immunoassays as well. It doesn't always have to be genetic. Let's say it was a bacteria like E. coli, or a pathogen or virus like SARS-CoV-2. It didn't always have to be genetic. You can also use immunoassays, and we have done that as well. We are equipped with a BSL-2 lab. This means we can handle things like E. coli, SARS-CoV-2. It means that we can't handle Ebola. That's a higher class than we have. So there are some pathogens, but it should be said that ZP is set up to be able to handle quite nasty sort of pathogens. I would say biology is more dangerous than chemistry. Biology is the world of viruses and viruses and bacteria. Not that E. coli is particularly dangerous. Whereas chemistry, yeah, it seems on the grounds it is dangerous, but as long as you take the right protections, you're generally okay. You're also okay if you take the right protections in biology. Anyway, that said, I need to move forward quite quickly. So we're quite set up to do amplification and detection. Sometimes we don't actually do that amplification. We just detect the pathogen directly. And we also have the biosafety cabinets and a unidirectional workflow purposefully for this kind of work. So what do I mean by unidirectional workflow? It's not enough just to say I'm going to do a electrochemical molecular assay. You need to have, physically, our setup is that we have a sequence of events that are going on in our lab as we do development. And if somebody's allowed to move forward along the workflow, but literally if they forget something, they can't go back. It's really important, because otherwise you're going to start carrying contamination back into the program. So we have a very strict unidirectional workflow through our labs, where we do the prepping, we do what's called a template addition, the testing, and then look at this testing. The testing is done in a clean room, but we have a sort of a class 5 bubble within a class 7 clean room. So it's, you know, it's super serious. And then, you know, we do the amplicon testing, and you can see that the person is very gowned up, and it's not just to protect them from the, let's say, the assay. It's actually to protect the assay from them. So we don't want to interfere. You know, one of the biggest sources of contamination when trying to make sense of molecular assays is the person themselves. They're full of genetic material. At ZP, we've created electrochemical biosensors in many formats. These are just a couple of them. So we have done this quite a few times. We've done point of care for viruses, point of care for mammalian, and we've also done multi-analytes. So we do, you know, it's not just enough to say, you know, is it the RNA, DNA, are we going to do an immunoassay? You know, we do have a quick look at, you know, the pathogen of interest. We do have the golden standards. Now, there's no such thing, to be frank with you, I'm absolutely sure of this. These gold standards in, you know, in molecular are not so golden as people think. They're very time consuming. But we would look at, you know, we can look at an assay by fluorescence, and we can also look at an assay by electrochemistry. I think they stack up really quite well. I mean, if anything, when Abbott first came up with when Abbott first came up with a SARS-CoV-2 test during the pandemic, I think it had an assay time of something like 60 minutes. We were doing similar work, and we were getting the assay time down to sort of 20, well, first of all it was 30 minutes and 20 minutes, and then we're down to 10 minutes. So electrochemistry, because if you're doing an amplification, you're basically doing a sort of, you're looking at the signal, and as the raw material, let's say, is being amplified, the signal starts coming up exponentially. And people look for this kind of critical time when they can say they can call the signal. So we can do that in real time as well. And so if you've got a high genetic load, then the assay time is shorter. When it's a small genetic load, the assay time is longer. So, but I think that, let's say fluorescence and electrochemistry stack up pretty well. The one thing about fluorescence is if you're going to make a point of care device out of it, you have a mechanical burden because you have to shield that entire assay from the ambient light. So I do prefer electrochemistry. And if you have a biology background, you're used to fluorescence, you'll make a fluorescence point of care device. If you've got like a sort of an electrochemistry background and you come from the sort of world of low cost glucose strips, which we do, then we would obviously prefer electrochemistry. This is a case study that we did where actually we did a pathogen detection actually on the breath, and we did the whole kind of hardware. Even got this, I know it's CE marked, so it was pretty serious, and we were glad to get that. At the heart of this cartridge is a electrochemical sensor. We were instrumental in packaging all this up, making all this essentially work, and that was sort of non-thermal. So some of these kind of PCR and lamp assays require a source of temperature. That was non-thermal, and it also didn't require the as I say, non-thermal, and also lysis. If you're going to do a genetic assay, the molecular material is often sort of within that cell, and depending on the target, it could be within the nucleus, but at least it's within the cell. So you do have to, if you're going to go that route, you have to do lysis. That's what we do. We do lysis, we do amplification, then we do detection. What we try to avoid is lots of individual compartments. We do try to do this in a very kind of people talk about lab on a chip. Lab on a chip for me is a bit of a bad term because it kind of suggests complicated workflows remain complicated and get reduced to microfluidics. No, if you're going to reduce something, if you're going to shrink it, you have to rethink it. And so we do end up coming up with simpler assays. This is the portable device for breath analysis. We also worked on mammalian, things like LAMP and PCR are assays that we do for amplification. This particular device, I blurred it out, but it did have temperature zones on it because we were doing thermal amplification of the molecular material before we were actually then doing electrochemical detection on it. And we were doing things like this was made for making an immunoassay, but we would use our gold electrodes to tether material onto the electrodes. We're very good at at doing multiple assays, and the manufacturing techniques that we we impose are also very scalable as well. So if people want to detect multiple multiple pathogens at the same time, ZP will understand what you're talking about, and we do have experience of. The previous one was we were doing 2 at the same time. If people want to do more, I'm sure it's within our toolkit. In fact, here we're trying to do 1, 2, 3, 4, 5, 6 handheld device. You can see with 6 tests going on. Now, I'm sorry to jump questions a little bit. Somebody was asking, I want a carbon working electrode and a carbon counter electrode. I generally don't recommend it because when you're making, they're specifically asking about screen printed electrodes. So with screen printed electrode like this, you've got, sometimes people put a small drop on there. It might be 50 or 30 microliters, so it's a small drop. So the way you set it up, and I have linked to the electrodes I'm recommended. When you set it up, you have a working electrode that's carbon. So that's, the thing that you're focused upon. You have another electrode in the ZP, let's say, material set. The counter electrode is silver chloride. That means that if on that carbon electrode you are oxidizing something, on the counter electrode you're reducing silver chloride to silver, and that's not, silver's not a soluble product. If you were reducing at the carbon electrode, then that means you're oxidizing at the counter electrode, and silver's becoming silver chloride. Again, silver chloride is not a soluble product. It's really important when working with screen printed electrodes and small solutions that you don't have a reaction happening on your counter electrode that's producing a solubilized material. Because what it'll end up doing is it'll end up diffusing across your working electrodes. So, for example, I've seen situations where the counter electrode was carbon or platinum, and it was producing hydrogen peroxide on the counter electrode because it was reducing oxygen. That oxygen was diffusing to the working electrode and effectively then being oxidized at the working electrode, which is then driving the counter electrode. So you have a chemical feedback due to the material on the counter electrodes. So when you choose carbon, platinum, and gold, if I asked you what reaction is happening on the counter electrode, you may guess, but you don't really know. But when you make it definitely out of silver chloride, you absolutely do know what's going on that counter electrodes, and it's either the reduction of silver chloride to silver, which is insoluble, or the oxidation of silver to silver chloride, which is also insoluble. So we do it for a really specific reason. So really think carefully about going away from ZP's counter electrode being silver chloride. Equipment. If this person, to obviously use our electrodes, I recommend a potentiostat. It's the same list as earlier on. I do prefer, the nice thing about just using the products that we have off the shelf is they're actually low cost and high quality. Once you start doing bespoke materials, you will end up with high cost, low quality, because you need volume in order to get high quality. And if it's just customized, then it doesn't really happen. They'll need a cable, they'll need a connector, and that's it. Now the last question is, have we heard of the LMP 91000? We have. I put a link. I absolutely do not recommend this chipset. You absolutely will work for you, and you'll see that on our website we've done plenty of work for it. I will not support this material on our website. I'll just tell you it's there. I will not support it. This material on our website is 6 to 8 years old. It's not something that it's not a chipset that we use these days, but I just want you to let you know it's there. If you find something useful, it's great. I just put the word 650 millivolts there. The voltage that you'll need to apply to the working electrode versus the reference electrode is 650 millivolts. If you're using a ZP Generation 1 sensor, honestly, save yourself some time. Just get this single purpose board. I've linked to it here, but it's your choice. Because this board will really, if you program it right, will do amperometry, will do voltammetry, do potentiometry, do impedance spectroscopy. I did ask these guys to come to our workshop. I'm asking you again, come to the workshop. I do have 2 people coming from Australia. So people are coming across the globe. Again, 650 millivolts is the potential that you need to apply. I've linked to the glucose sensor twice because one of the links has data and the other link has the actual sensor I think you need to purchase. And I suppose I've just focused in on glucose just to say, just get going. Honestly, you'll outthink yourselves. Just get going. You're only going to essentially start learning. You've done so much research at this point. You're only going to learn by starting. So question number 1, I think the resolution you can get is 0.1 millimolar. How to convert current into concentration. I've given you some standard curves and shown you a kind of a simple linear regression procedure. Question number 4, right? So baseline yourself on a screen printed electrode, add this new novel material and show the improvement. That would be my sort of suggestion. For RNA detection, ZP is very experienced in it. How do we compare up against the gold standards? Well, don't forget, we're also not trying to compare ourselves against the gold standards. We're trying to make handheld point-of-care multi-analyte devices. There are no gold standards for it. Don't just change the counter electrode to carbon. We chose silver chloride for really strong reasons. And yes, at ZP, we've definitely heard of an LMP 91000. It's a fine potentiostat. It's not one that we use or recommend. I have given you some links to show you some old material that may help you. But the voltage you need is 650 millivolts. I just want to say thank you very much. My apologies for speaking so fast. Literally, we've done 7 questions in 25 minutes, and I have another meeting starting in 5 minutes. Okay, so if you've got any questions for ZP, don't hesitate to reach out to us. Okay, thanks very much.